So via NMR and infrared. All right. So let me talk about what NMR is, what infrared is, and then we're going to do our first since we're already upstairs. And I'll show you the instrument. We're going to run 3 samples. We're going to run the crude, infrared on the crude. We're going to run infrared on 2 other samples, and then we're going to take an NMR of all 3 of those samples as well. So what is NMR? That's an acronym for nuclear magnetic resonance. Right, and what NMR, what we're going to be doing today is what we call Proton NMR. So that's going to strictly look at, and if sometimes you'll see it abbreviated like that, 1H NMR. That's strictly looking at the hydrogen nucleus. Right, so what it's going to tell us is the carbon hydrogen framework of aspirin. So this is aspirin. If you remember the structure, it looks like this. You got an aromatic ring here. You got a carboxylic acid out here, and then you have an ester on this side. Right, so you have protons here. Ooh, that's a bad color for this color paper. Right, you got protons here, 3 hydrogens here, and you know, yeah, thanks. You got hydrogens on the ring. So what the proton NMR is going to tell us plainly is 4 things. It's going to tell us how many different types of hydrogens are in this molecule, what they're located next to, what types of carbons they're located next to, what type of carbons they're located on, and how many hydrogens each signal represents. So in this NMR, excuse me, of aspirin, what we're going to see is that each one of these hydrogens is what we call non-equivalent. So they're all going to give their own specific chemical shift. They're all going to show up in a certain place. And that's too similar, sorry. Keep that. So on the ring, you got 4 different types of hydrogens. And so you're going to see 4 signals for those hydrogens, right? Because all of them are different. And then you're also going to see a signal for that CH3 in the NMR. So the aspirin NMR, it should have at minimum 5 signals and maximum 6 signals, because this proton right here may or may not show up on the aspirin NMR, right? So I'm not gonna go into the theory or what the spectrum is gonna look like. If you watch that video, the NMR video that I sent out last week, you saw what a spectrum looks like, and we're gonna see it today in real time. We're gonna actually take our aspirin down and run an NMR. So that's that. We're going to see at a minimum 5 signals, maximum 6 signals. And if there's any salicylic acid left over, right, we got any salicylic acid left over, which looks like this, we're going to see that too. And one dead giveaway for salicylic acid is this OH proton always shows up. So this is definitely going to show up. If there's any salicylic acid left over in our sample, you're going to see that carboxylic acid proton show up somewhere between 10 and 11, right? Each one of these hydrogens is going to show up at a different place on the spectrum. For aromatics, these show up between 6 and 8 parts per million, and I'll explain that when we get downstairs. For the carboxylic acid, that's between 10 and 12 parts per million. And then this, because it's next door to a sp2 hybridized carbon right here, the carbonyl carbon is sp2. That's going to get pushed what we call downfield, and I'll explain all that when we get downstairs. And those are going to show up somewhere between 2 and 3 parts per million. All right, so that's the quick and dirty explanation of the NMR. And then for the infrared, which we're going to do first, so for the infrared spectroscopy, what we're going to do is use, sorry about that. Let me get my writing together. We're going to use an instrument called an FTIR, right? Fourier transform infrared. And it's going to bombard our samples with infrared radiation. Now with the aspirin, let me redraw it again. We have several things that are going to show up. Right, so what infrared tells us is what functional groups are present. Right, that's the bottom line. When we take an infrared, we're looking for functional groups because every functional group has a specific infrared frequency where it's going to absorb radiation. Right, so we have in aspirin 3 main functional groups. We've got an ester, we got a carboxylic acid, and then we have an aromatic ring. Right, so those are the 3 functional groups we're going to be looking for in the infrared. And I'll explain where they show up and all that stuff. The aromatic stuff is going to show up somewhere around 3,000. I'm just going to give a ballpark and say about 3,000 to about 3,300. And it has a specific type of absorbance that you're going to see. All right. And then the acid and ester, they show up somewhere between 1,700 and 1,800. And this is in reciprocal centimeters or wave numbers. Right? Because that's 1 over the wavelength. All right. So what we're going to do now, any questions before we actually start working? I'm just going to set up, we're going to set up one sample of the crude aspirin. We're going to take an infrared of that, and then we're going to take an infrared of one of our other samples. So we got Eli here. He's going to help to take one sample, and then I'll do the crude sample. All right. Any questions?
Yes.
Go ahead.
Where is the document where we're going to write down all our information?
Yeah, well, so you're not writing down this specific information. What we're doing today, the other assignment was just an assignment to get you acclimated to understanding the concepts of NMR. Right? I don't know why it's not showing in Blackboard, but I got to reopen it. So I'll open it up. You'll have until next week to finish that. But today, what we're doing is actually collecting data for your report. So the infrared data we collect today is going in your lab report. And then the NMR data that we collect, that's going in your lab report. That's going to be in your appendix of your report. So what I'm going to do, once we collect the data, is save it and upload it to Blackboard so you'll have access to it. So everybody's going to have access to these data, and you can include it in your appendix. It's actually quite a big chunk of your grade if it's not there. All right. Does that answer your question?
Yes. Okay,
great. All right, let me stop sharing. I'll share this document too. All right, so the infrared, the FTIR is here. This is a tiny instrument compared to what a traditional infrared looks like. There's a diamond tip here, and it's that diamond tip that's going to come in contact with the sample, and then the radiation is going to come from here. right? There's an aperture there, and that's going to irradiate the sample. Well, let me take that back. There's an aperture here, but the radiation is going to come through the tip. And the tip is going to come in contact with the sample. And while it's bombarding the sample, the functional groups that are going to absorb whatever wavelength hits it, those are the functional groups that are going to show up in the actual infrared spectrum. All right. And I'm going to clean that diamond tip off. There's a diamond tip on both sides. There's a diamond on the plate, and then there's a diamond tip on the arm. I'm going to clean that off too. And now I'm just going to run the background. So there's nothing on here, right? And so I'm going to collect background first. Hopefully y'all can still see that. And now you see the background, it's just crap. All right, so I'm just gonna hit start collection. And to run a sample, it takes 32 scans. So the background is to help me or help the instrument filter out carbon dioxide in the air, water in the air, any type of moisture. It filters all of that out. So this will be subtracted from the sample that we actually run. All right, you can see on the x-axis from 600 to 4,000 wave numbers, which is in reciprocal centimeters. That's relative to the wavelength, right? Because the wavelength is normally measured in nanometers. And so what that tells me is the wavelength, which from that I can calculate the frequency of the radiation that's being absorbed at a particular spot on that axis. All right, so this is almost done. And once I collect the background, it says prepare, okay, blah, 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 done that. So now it says prepare to collect the sample. So I'm gonna lift this arm up, move it out of the way, and now I'm gonna put my sample back on here. Sure, that's fine. So now I'm gonna put the sample back on, a little bit of this crude aspirin. I'm gonna put it right here on the diamond. All right, I'm gonna take the arm, boom, and put it right on top of the sample and turn it until it clicks. All right. So now I'm ready to run the sample, and I'll just click OK. And I'll be able to so now the sample is ready. So now you can see right away, you see some peaks in here that look different from the background. So I'm just gonna click start collection. And it looks crappy. See how the baseline is all fuzzy looking? That's on purpose because this is crude. It's not pure, so that's other crap that's in there. So I'm gonna click start collection, and it should start by collecting 32 scans. So you can see over here in the corner, I don't know if you can actually read that, but right here, it's collecting 32 scans. And right now we're on scan 6 of 32. All right, any questions? All right, and you can see right here, about 2,400 to about 3,000 in that area. That's your aromatic stretching. So on that aromatic ring, those carbon hydrogen bonds, think of that, those bonds being like on a spring. And so as the bond is naturally stretching back and forth, the minute the right wavelength hits it, it's going to excite that bond. And then as it excites the bond and it gives off energy, that's what's picked up on the by the detector. All right. And so down here, and I'm gonna pick peaks real quick just so you can see. I'm gonna do a peak, find peaks. So you see down here, you got these peaks down here, 1602, 1660, 1745. One of these is probably gonna correspond to the ester, and one is probably gonna correspond to the carboxylic acid, because it's still aspirin, it's just crude aspirin. So one of these is probably going to correspond to the ester, and one to the carboxylic acid. So that's that. And then down here, you can see these aromatic peaks show up right here also. All right, any questions about that? So I'm going to save this. And then here, and then this is a non-destructive method. So if you actually wanted to save this, you could just break it back into your sample container and start over. So I'm going to get as much of this solid off as possible. All right. And I'm going to hit this with a little ethanol to clean it off. You want to make sure all that solid is off of there, because what you don't want to happen is to dissolve the solid up and have a film or a residue on here for when you're running your next sample. All right, so that's that. I also need to clean the arm because it was touching the sample as well. So I just put a little ethanol on my CHEM wipe, and I'm going to clean that off as best I can and make sure there's no leftover crude aspirin on that. All right. Now let me show you this again because I didn't have the actual plate on there that was supposed to be on there. Let me make sure it's on properly. All right. So you can see now, you see that little hole in the middle, that's a diamond. That's a diamond on the plate. And then there's another diamond in the arm. Probably see it better from back here. All right. And so when those two touch, the radiation is going to go through the diamond that's on the plate, and it's going to penetrate that, go through your sample, and then what's in the arm is going to be able to detect the sample and also the different functional groups. All right. So let's run another sample. I'm going to let Eli run the other sample that's up there. So same thing, take the spatula, clean that off. Take the spatula, add some directly to that diamond on the plate. Just enough right there. Oh, it's actually too much. Like that. Yes. A little bit more. Perfect. So put that right on that diamond. All right. You can smooth it out a little bit. Don't worry about that. It's not going to pick that up. Perfect. And then also move the arm over like that. Turn it so that it contacts the surface. You'll hear it click. Stop right there. Okay. So now what we're going to do is collect another sample, and we're going to call this sample 1. Yeah, that's on there. 1322-02. So go ahead and have a seat. Just click OK. All right, so we're going to collect this sample and then just click OK. It's going to give you a preview after one scan. And then up top, just click Start Collection. Right. Okay. So you can see this is a lot cleaner. You can see the baseline here is a lot cleaner, and the peaks are a lot sharper. So that makes it a lot easier to interpret as opposed to taking a spectra of a sample that's really messy. All right. So right now we're at 20 scans out of 32, and again, you can see right away. You see your carbonyl section down here. And down here, you can see your aromatic section. It's much cleaner than the original sample. Well, crude sample. All right. Anybody got any questions? Just click. yeah, click yes, add to a new window. All right, and then type, does it say window 6?
Yes.
Yeah, just click OK. All right. So now what we want to do is click find peaks. So you can see right here, you got 3 peaks here. And out of those 3 peaks, again, one of those is more than likely going to be your ester, and one is going to be your carboxylic acid. And there's one other peak that's important, and that's this one right here at 1181. That's the carbon oxygen single bond on the ester, right? So that's a really important peak too. So let's print this. So just hit print right there. These are, let me turn this around to the corner. So these little tubes right here, let me get in the camera. Can you see if I'm in there? These little glass tubes are NMR tubes. Yeah, perfect. Right, it's got a little blue cap on it. And so what we're gonna do is take some of our solid and put it into this tube. And then when we get downstairs, we're going to dissolve it up in a deuterated solvent and then run the NMR. And I'll explain while we're doing the NMR what's going on. So let's take sample. We're gonna take 3 NMRs. So get the crude and the sample 1, and we're gonna make up samples. So this is my crude sample. So normally when you have a solid and you want to take an NMR of it, you just take the tube, you take a pipette, and you just dip it into the sample. Right? So I'm dipping it here in the sample, and I'm gonna just take that and put it right into the NMR tube. I don't care if it goes down or not, because when I get downstairs, we're gonna add the solvent to this in order to push it through the pipette. So that's that, and then we're gonna make up another sample of sample 1. Same thing, pipette into the sample. Like that. And I only need a little bit, right? So that's plenty. Milligrams, I only need milligrams of this stuff. It doesn't have to be all super concentrated. Right? And then I'm gonna do one more, which is gonna be sample 2. All right, so put that here. Same thing. You can tell I did this for several years out of my life as a grad student. This is all, if you're an organic grad student, this is all you do, make stuff and take NMRs and infrared and mass spec. We have a mass spectrometer too, but we're not going to do mass spec because that instrument is a little bit more difficult to use. All right, so we got that. So what I'm going to do, can you put these back in the drawer up there that says Wednesday? If you open it up, Wednesday is actually written in the drawer. All right, so what I'm going to do is real quick clean off the FTIR. Okay, we are now downstairs in the NMR lab, and I'm going to give you a tour first. It's kind of loud in here because of the mass spec. This is the mass spectrometer. It's a QTOF, which is time of flight, LCMS. This instrument is probably close to $700,000. And mass spec, it allows us to look at like the molecular weight of a molecule plus whatever fragments it breaks into. And then this instrument is our NMR. It is a Bruker 400 megahertz. And you can see it has some little apertures on the top. Those are ports to fill it with liquid nitrogen on this side, liquid helium on the other side. And this is actually a giant magnet. It's a superconducting 400 megahertz magnet. And it has to stay at a certain temperature. It's got to stay cold, otherwise the magnet will quench and the instrument will be useless. So once a week, we have to take a dewar of liquid nitrogen and fill this thing up once a week. And then liquid helium, we fill it up once a year with liquid helium. All right, so this is a really cool instrument. So we're gonna get the samples ready first, and then we're gonna come back. And so I have my chloroform in my pipette. Let me find my camera. And I'm gonna take my first sample, which is here. I'm just gonna add the chloroform straight through that pipette that's in there and dissolve that up. So now you can see that sample is dissolved up. You can see the line. You normally want about 2 centimeters of chloroform in there, so that's fine. I'm going to dissolve up sample 2 the same way. All right, like so. I'm going to put that directly into that and just add the chloroform straight to it. Come on. Come on now. Stop playing with me. That's good. So that sample is ready. And then I'm going to take the crude. Sample 1. I'm going to take sample 1. Sample 1 is already falling out of the pipette, so that's great. I just need to add some solvent to it. I'm just going to add that right into the pipette. So whenever you transfer in a solid, this is the easiest way to do it. It's just to use a pipette, put some in the tip, and then put the solvent through the pipette. So that deuterated chloroform is a pretty expensive solvent. And what you're going to find out is that when we run the NMR, that it shows up at a specific place in the NMR. So the solvent shows up about 7.24 parts per million. So we're going to bring out, can you put that back in the food? It's 7.24. All right, so we're going to come over here. Type EJ is it's a Unix. All this stuff is on Unix programming language. So EJ is going to eject the sample that's in there. So just hit enter. And let me show you over here. You're going to see the sample that was in there pop up. All right, so that sample has popped up. So I'm going to take that out. You can see that it's on a spinner. Let me see if I get the camera right. There's a spinner here. All right, and it has some black and white panels on it, and that's on purpose because when the sample is inside the instrument, you have to spin it in order to homogenize the radiation that's hitting, right? So that's just to keep track of the RPM. So if you would, Eli, slide that spinner off of there. Just slide it straight down. All right, so that's the spinner, and that's the sample that was in there. So we're going to take the spinner now and put our sample in. So take this, I'm going to put this into here, like so. And then I need my depth gauge. This is my depth gauge. I always use this to know how far to push my sample down. So I'll push it down until it stops. Right? And when it stops, I can now put this into here. Now, I'm not sure if you can hear that, but it's actually, there's a little hissing noise. If you don't hear that, don't put a sample in because that's compressed air. There's a compressor across the hall. If you don't hear that hissing and you put that sample in there, it's going to drop straight to the bottom. So there's a cushion of compressed air that I'm just going to sit this here and it'll sit until I inject it. If you don't hear the hissing, don't put a sample in. What you'll end up doing, the sample will end up dropping all the way to the bottom of the instrument, breaking. Then you got to take it apart, take the probe out, and disassemble everything and clean everything and get the glass out. And so if you have to call the company for that, they charge you from the time they get in the car to drive to the airport. That's when that hourly rate starts. So for them to fly here, fix this, clean it, and go back, it's about 50 grand. So you don't want to just be willy-nilly over here because this stuff is not cheap. All right, so we're going to go back to the control panel. I'll take that. And on the control panel, hopefully y'all can see the screen. Let me move this out of the way. That's perfect. All right, so on the control panel, I want you to go to File up top and New. Yep. All right, so change that name to Sample 1, 322-02. Okay, take the dash
between 3 and 0.2. That's O2. And then, okay, so yeah, that's fine.
Oh,
And then, okay, so now we put the sample name in. There's a couple of things we need to do. Right there where it says experiment, you want that to say Proton. Hit, but click select. These are all the experiments you can do with this NMR. This whole page, scroll down. All this whole page of stuff, these are all different experiments you can do with this instrument, which is amazing. You can do all kinds of stuff. But we want Proton. So I want you to find Proton on here, right there. Click it and just click close. All right, so now we're doing a Proton NMR. Right there, the second command says set solvent. So click that. All right, we're gonna use CDCl3, deuterated chloroform, right there at the top. That's the solvent we use. You have to tell the instrument that so it'll know where to locate the material and where to lock the signal. All right, and so we're gonna change that directory too. Change that, go down, not that one, that one. Yeah, change that name to Russell, where it says call you. Just click outside that.
Click right here.
And then change it to Russell. That way I'll know what to upload to Google Drive.
Like that's good.
Yep. Just click OK. Boom. All right, so the screen is blank now. We got a new file set up. So now we want to lock the signal. Right here, you can see where it says lock on this other panel. Right here. That's not, so the lock is not on. What the lock does is it locks onto the deuterium in the sample, and it keeps the magnetic field in the instrument from drifting. So that's why we need a deuterated solvent, because you lock onto deuterium in the solvent. So go where it says lock over here, very user friendly. Just click lock and find your solvent, CDCl3. Yep, and then click OK. All right. So now it's going to lock, and it'll look down here in the bottom left corner. It'll tell you all the progress. When it's done, it'll say either finished, succeeded, or done. So right now it's still locked. It's still finding that material. Hold on. Same mistake we made yesterday. You got to put the sample in. So type IJ for inject.
And then enter.
Yep. Click OK, because it's not going to lock.
If it's not in there.
Yeah, so click IJ or type IJ. You'll hear a click. All right. So now click lock. My bad. And find the solvent. Boom. And click OK. So it's gonna again, the same commands are down here. You want to find the deuterium, lock onto it, and it's going to tell you either done, succeeded, or complete, or finished. My bad, not complete, finished. So this is a very sophisticated, right? So now you want to click tune. Which, if you notice, everything is in order.
So tune.
No, go back. Just click the button itself, the tune button. Yes, not the menu button. Because there are other commands that come up, but you don't need them. Okay. So once you click tune, you'll see down at the bottom left, and then it'll tell you what it's doing. And then on the screen, you're gonna see a parabola come up. Okay. And the tuning, see that? So boom. So now that's done. Once you see that, it's finished. Okay. Right? That's tuning the probe to your proton sample. And I'll click spin.
Just click it.
Yep. And RO on. Very top command.
This one right here.
Yep. And now what you're gonna see down here at the bottom is a red arrow come around there where it says sample. That's how you know it's spinning. All right. Once you see that, you know that the sample is spinning. So look down in the bottom left corner, it says done. So now click post all, CHEM, and then leave it. So shimming is the hardest and it takes the longest out of all the commands, because what you're doing when you're shimming the coils up in the instrument is you're homogenizing the magnetic field. So you want to make sure that the magnetic field inside that canister is the same no matter where that sample is when it's spinning. So the shimming takes longer. It used to be done by hand. This was a physical pattern on the table. And that knob, you would shim the Z1, Z2, and Z3 axis until this display
like that.
did move in. I don't know why it's not sweeping. I'm not sure. But it's just not showing. But it is shipping. And again, bottom left corner, that's where all your commands and everything is happening. So when you look down there, if it says it's done, that's when you know that it's done. All right, anybody got any questions that's watching?
I guess my question is, are we supposed to be filling in data for this somewhere?
No, we're collecting data here for the lab report.
So succeeded, is that done, or it will say done?
Yeah, so succeeded, yeah. So no, this is all collection of data so you can put in your lab report appendix, because all these are the samples that we actually made. So the NMR data that's going into your lab report is going to come from these samples. And the infrared, on the lab report where it says spectral data, all of this is your spectral data. So this is the stuff that we collected to add to that appendix.
So now press the photos
So
off.
it's all, yep. Does that make sense?
Yeah, it does.
Okay. And then gain. So what the gain is doing is now setting the receiver up over here, this box on the floor. That's the receiver, and that's going to talk to the magnet. But we have to set the receiver gain so that they'll know how to communicate with each other. All right. And then once that's done, click go. So normally for a Proton NMR, you want to do 16 scans, and what you're going to see on the screen is a graph start growing in, right? Because what happens is every scan is a pulse of radio frequency radiation that's hitting your molecule, and it's hitting it and affecting the magnetic field around the hydrogen. That's why we call it Proton NMR. So every time it pulses, you hit it with radiation, but in between the pulses, the protons relax, and then you hit it again. So you keep doing that for 16 scans.
Okay. That shows it right there.
Yep. Yeah, so now we're on scan number 7 coming up. Right, and then again, this right here is not readable. This is what you call a FID, a free induction decay, right? But we don't know any information about the spectrum from this. So we're gonna have to convert this. After it's done, we'll convert it using a Fourier transform, but we don't have to do it. The processing software do it for us. All right, so now we're at 13 scans. And this is a good sample too. If it was not really concentrated, that FID would be a lot more fuzzy around the edge.
Like here.
Yeah, it'll look like crap. Okay, that's how you know your sample is not concentrated enough. Okay. All right. So now that's done. So now you want to transform that. So you want to type in TR
Right here.
Yep. Type in TR and then hit enter, and then type in FT for Fourier transform. And type in, so now, hold up, before you do that, you can see on the screen, everything is upside down. That's because it has to be phased. So type in APK and enter. And it's gonna turn that right side up.
Okay.
So now, that's phasing is a part of the processing process, or the processing. So click that double arrow that's pointed up and down. Come on over to the right. Yep,
Oh,
right
this
there.
right here.
Click it, drag the spectrum down to the 0 and the right there. All right. So now this is the well, I would have been bad. So this is what the spectrum looks like. So now click that 8, multiply, Aspirin. Okay, click it again. Okay, great. Click 2, divide by 2.
Sure, yeah.
Right there, yep. Perfect. So now what you see in the spectrum, this is actually really clean. This is great. So the aspirin peaks are here. These are your aromatic protons. So those 4 H's that I showed you upstairs on the ring, each one of these signals corresponds to one of those H's.
The thicker ones, not the tall one.
Yeah, if you click the button, the magnifying glass, the plus it.
This here.
Oh,
right there.
Click it again. All right, you can see that those peaks look, they're not just single lines, right? They're
Yeah.
split up. Okay. And that's because of how they're oriented on the ring next to each other. So they split each other based on their magnetic field. So click the double-sided horizontal arrow. Come on over, right there. Scroll down, grab and drag. Stop right there. So this right here, that's the methyl proton on the ester. So if you look at the structure of aspirin, the ester part, that's the CH3 that's attached to it's the acetyl proton. All right. So that's a really good sample. It's very clean. Scroll back down to the aromatic. So right here, if this was really dirty and if there was still salicylic acid left over, you would see all of these areas that are empty. You see salicylic acid, aromatic peaks in there, but you don't see that. So that's great. So click stop. And click EJ. And we're going to see, I'm sorry, type EJ. You see the red stop sign button up there?
Oh, yeah.
Yeah, click that. Yep. And then type in EJ and eject the sample.
Will it pop up anything about the quick stop?
Yep. And you'll see the sample pop out. And let's do the crude next. Because I want to show from the crude, I want to show you how you know that there's leftover salicylic acid. So take so just take that yep. Cap it off. And then take that label off, and then you can just put it into here. Yeah, you can just stick that back in the cup. Yep. Take that out. Yep. Sit it back down in the cup, and then put that through the spinner. And let me get the depth gauge. Sit it in there, and then make sure it's at the right depth. Boom.
Just need to be on a certain.
That's fine. So now I'm going to put this into here and just go over and type. So now we're going to do a new file. So let's save that. Yeah, so go to file and then save as. And then click OK. And then click OK. Hold on, go back. Yeah, close. Change make the R and Russell capital letter because this is not reading that directory. Yep. What does it say? Click cancel and go back. Change the name to and click OK. And then is it still not? Just cancel. Let's save it somewhere else. Close it. Yep. Close. Cancel. And then go to file. Save as. Save data set. Let me see. Save other. Oh, that's right. Right there.
Right here.
And then go to OK. And then take Russell off and just put NMR. Just do it. Put in an NMR SU. No, that's fine. Take all that off. Take the slash off too. We'll just save it in the main folder. And then just click OK. We'll be able to find it. All right, so now, yeah, file, go to a new file, and then just go ahead and type RJ after you set it up, because all the parameters are gonna be the same except the file name. So yeah, so change that to crew 322-02. And then everything else, the solvent and all that stuff is all the same. That's 02, yes. Yep, I just click OK. And then type RJ. So when he types RJ, that's gonna tell the magnet to eject the sample. So you saw the sample go down. So that's that. So now we're gonna run through the same process for the crude.
And you do, is it lock?
Yes.
Same thing.
CDCl3, yep, it's okay. All right, and then you just, again, following those commands up top. All right, anybody have any questions while we are running the second sample? But what I want to show you with the crude is what the actual,
Now tune.
yes, what the actual sample looks like when it's not pure and when it has leftover salicylic acid. So we're going to see that. All right, so tuned up. Now just put span and RO on.
What is the RO on? Or
Rotation.
Rotation, okay. So if it's spinning or like spinning, rotation, what was that? Is it, that's a rotation on and off, so.
Yeah. If you leave it off, then the sample, the spectra is going to be wobbly because it might bombard one part of the sample with radiation, but the other part is not getting.
Okay.
So you spin it like this. If you were, if I had a barbell and I just started shooting at you, I might catch you on the shoulder or the side, but if I spun the chair around and shot at everything is getting.
Okay.
So that's the purpose.
So now the shim.
Yep. And again, shimming takes the longest because you have to homogenize the magnetic field within the magnet. All right. So that's why we're going to take the crude, and then we're going to run one more sample, but we'll log out, and I'll just post the data for that sample. But we'll stay logged in while the crude is running, because I want you to see what the leftover salicylic acid, where that shows up. Yes. All right, it's coming. It takes a while to shim. And it's the Proton and game.
Dr. Russell,
Go ahead, boy.
you said something was due next week. What exactly is that?
Yeah, the NMR assignment that's in Blackboard, but for some reason it's not showing, so I need to open it back up. But I'll open it before I'll open it before I leave today. That way y'all can see it. And then tonight I'll upload this recording and the spectra and all that stuff too.
Okay, thank you.
Yeah, you're welcome. All right, so now we're running, this sample is running, and it's gonna be a couple of minutes before we can actually see. But it's gonna look different from the first sample. That first Aspirin sample was extremely clean. There was nothing left, and it was all Aspirin. And that's a testament to the recrystallization process. Because whoever purified that sample did a good job. All right, so you can see the pre-induction decay going in. also see another thing that's really important. You can also see the temperature. Right? Yeah, that's really cold. Like really, really, really cold. What is that? -23?
Yeah, that's what I was trying to figure out, because isn't it Celsius and Kelvin is 270 plus or something like that?
So I want to go to Celsius. I need to subtract that temperature from 270. I got to subtract 270 from that. So Celsius is Kelvin is Celsius plus 273. Is that right?
Yeah, I think so.
All right.
And then it goes from Celsius to Kelvin. Celsius minus 273.
Yeah.
Like all those.
Yeah. So this is the crude sample, and it's done. So you want to type in the transform. Okay, and then type in FT. And then again, it's out of phase, so you need to type in APK. And you want to drag it down, so that double-headed vertical arrow. Yep, drag that down. Okay, great. Now just hit the multiplier. Just hit it by 8. Again. All right, perfect. Now, in this spectrum, you can see more peaks, right? Down here, here, and here. Those smaller peaks, those are impurities. That's leftover salicylic acid in this sample, but it's a crude sample, so you expect that. There's not a lot left, which is good, which means that when we made it, the reaction almost went to completion. So you almost used up all of the salicylic acid and the reaction to make aspirin. All right, so we're gonna actually stop here. We got one more sample to run, and I'll post the data to Blackboard. So what I need you to do when the data is posted, I need you to save it, and I need to see this in your appendix of your lab report, right? Just all the spectral data goes in the appendix. It's a big part of the overall grade, so if you don't put it in there, it's gonna, I mean, it's either there or it's not. So you want to make sure that you have this in there. So the infrared data and the NMR data both need to be in your report. All right. Any questions?
I have a question. When you say like the data, do you mean like you're going to post like these graphs for us to add in?
Yeah, I'm going to post the spectrum into Blackboard as a PDF document, and then you can copy them and paste them into your appendix.
Okay, thank you.
Yeah, you're welcome. Any other questions?